Hello, so in this video we're going to talk through something called the golden section search, and it's actually a really nice algorithm that doesn't involve any kind of differentiating whatsoever, just to essentially try and find a minimum. Okay. By the way, I'm going to talk all the time now about minimizing. Okay, because of course you can convert a maximizing into a minimizing just by minimizing non-linear programming problem just by multiplying through by -1. But from this point on, we're going to kind of talk only about minimizing. The reason for that is with the golden section search, okay, if I talk about minimizing and maximizing at the same time, so I talk about both cases at the same time, it's just going to lead to so much confusion. So much confusion, okay. So what I'm going to do is just talk about minimizing and minimizing alone. Okay, but hopefully you can see how it relates. If I want to maximize a problem, hopefully you can see that instead of just finding the lowest function value, I need to find the highest function value if it's for maximizing. So for minimizing, I want to find the lowest function value. Yeah, I've got something like that. I want to find the lowest function value. Or for maximizing, I want to find the highest function value. That's the only difference. I'm just going to talk about minimizing so don't get confused. Okay, the golden section search is actually a really, really nice algorithm. Okay, and it basically works by essentially considering an interval, so something like that. Okay, so an interval of the function, and it basically makes the interval smaller and smaller and smaller until it converges at that point. Okay, until it converges at that point. All right. Now the only thing is, you have to make sure that the minimum actually lies in that point. So say, for example, if you have something like this, or even if you just consider this function again, say, for example, if you consider that interval, that would be no good because fairly obviously a minimum doesn't lie in that interval. You have to consider an interval where the minimum will actually lie. You also have to make sure, and this is a crucial part, if you have something like this, for example, okay, where there's lots of minimums, okay, lots of minimums and maximums, you have to make sure that there's only one minimum that occurs in that interval. So, for example, if you took an interval from here to here, or from maybe if we put it over here, okay, you can hopefully see that there's a minimum there and a minimum there. There's two minimums within that interval. That's no good, okay. The golden section search won't work in that case. You know, you're probably going to make a mistake. You have to basically make sure that there's only one minimum, which is in that interval. Okay, and that's a really crucial thing. And we call that, if there's only one interval in there, we call there only one minimum in there, we call that unimodal. So, okay, let's start talking about the golden section search. It's a really nice algorithm. Okay, so basically I'm just going to draw something like this in. Okay, and the idea is this is our interval. Okay, so this is a function which lies on x and y plane. So it's a one-dimensional search, so I'm only going to consider moving x. All right, so I'm only going to consider moving x. So the x-axis is obviously the horizontal axis. Okay, well basically this is my interval. So I've got an interval which kind of comes down here. Okay, so I've got an interval that comes down here, and this is my lowest point of my interval, the lowest point of my interval. So I'm going to call that x low. This is my x point, which is the lowest point of my interval. So I'm going to call that x low. Likewise, this is the x value, which is the highest point of my interval. So I'm going to call that my x high value. Okay, so I've got x low and x high, and then basically what I do, and this is the really crucial bit, is I then put 2 points in the middle. But these 2 points in the middle are defined in a very, very special way. Basically, the distance between x high and this point over here is exactly the same as the distance between x low and this point over here and this point over here. Okay, so these 2 points, these two values are exactly, these two distances are exactly the same. Okay, so the red distance is exactly the same as the blue distance. Okay, so that's basically the whole point. And I'm actually going to call this distance here x1, okay, and this one here, or the value here, and this x value here, I'm going to call it x2. All right. Now, the other most important thing about this, the reason why it's called the golden section search, is because the distance, so this red distance, say, compared to the overall distance. So when I'm making a comparison, I'm talking about a ratio. Okay, so the ratio of that red distance compared to the overall distance has to be a particular number. And that particular number turns out to be something called phi. That particular number comes out something called phi, and it's actually 0.618. Okay, and this is, or it carries on for, it's like pi. It carries on forever, infinite number of decimal places. But it's a really nice number. It's a really nice ratio, and it comes up everywhere in nature. Okay, it's a really pleasing number. But basically, yeah. So the ratio of this red distance. So what is this red distance? Well, it's going to be x2 x2 minus x low. Yeah, you happy that that's the distance of my red distance? Okay, compared to my overall distance of my interval. So in other words, x high minus x low, that's the distance of my overall interval. That distance has to be phi. And likewise, I can also say the same about the blue distance. So, sorry, that's equals in there. It's equal to phi. I can also say the same about my blue distance. So in other words, my blue distance is going to be x high minus x1, okay, compared to my overall distance of my interval. So x high minus x low, that's my whole interval. That's also got to be equal to phi. And actually, we're going to use these later on, or in just a moment, when we come to actually refining the interval. Okay, so the idea is that basically now what we're going to do is look at these two function values at these particular points. So this function value at x1, okay, so what's this function value at x1, okay, and this function value at x2, so we're going to measure the function value at x2, okay, and we basically look at which one is, well, we're minimizing, so therefore we want the lower function value, right, because the minimum will be the lowest function value at that, the lowest function value, minimum will be the lowest function value, so therefore we want the lower function value of the two. So therefore we want the lower function value of the two, so therefore the lower function value of the two, hopefully you can see, this is below x, this is below the blue one, so in other words, the lower function value will be at x2, so x2 will take the lower function value, right? So in other words, what we can say then is we can just ignore this part of the interval, so we can ignore this kind of we can ignore this part. We know that the minimum isn't going to occur down this end. Okay, so this is effectively now going to become our new interval. Okay, so from x1 to x high, that is going to become my new interval. Okay, but if you remember with the golden section, or as you can see, hopefully, with the golden section search, I also need another point in here. So in other words, okay, let's just do a little bit of updating. So this is now my new interval, right? This is now my new interval. So in other words, x1 is no longer my x1 anymore. It's now my x low, it's my lowest value of my interval, so therefore it's going to become x low. So in other words, I now need to define a new point in here, which is x1. Well, how can I define a new point in x1? Well, basically, I need the requirement that the distance between x high and x1 is exactly the same as the distance between x low and x2. Okay, in actual fact, I've come up with a formula over here. Okay, I've come up with these formulas over here, which allow me to find x2 and x1. Okay. Likewise, the same would, it's the same kind of principle for. Hopefully, you can see that if x1 is the lower function value, as you're just about to see, actually, I'll show you in x1 is the lower function value. So just bear with me for that. Okay. So basically, we need to do a little bit of updating. Okay. So what will x1 be? What is the value of x1? Well, we basically need x1, so we need to use this formula because that's got x1 in. So if we rearrange that, we basically end up with, well, what do we end up with? We end up with. So I'm rearranging this formula here. I've literally just rewritten this. I've just written phi on the right hand side instead of the left hand side. Okay, so I'm just going to multiply through by x high minus x low. I'm going to multiply through by x high minus x low. Okay, and I want to find what x1 is equal to. So if I then swap x1 with this thing here, I end up with that is going to be, so this is minus, and that's going to be equal to x1. So x1 is going to be x high minus the distance, the ratio from x high to x low, and that kind of makes sense. So x1 is of course the distance from x high. X1 is going to be that distance there, so from x high, so I'm measuring from x high, right? So it should be x high minus minus 0.618 times the interval of the length of the whole interval, okay? Because that's what I need to make sure that ratio is preserved, all right? But basically that's just kind of how to work it out. So I've got x1, okay, I've just worked out what x1 is. Okay, so let's have a look. So now I need to look at which function value is lower out of x1 and x2. Okay, so x1 and x2. So let's have a look. So let's measure across. Look, now x1 is lower. So therefore I know that I can just basically discount this section over here. I know the minimum isn't going to occur in this section over here because I want the minimum value. So I know the minimum isn't going to occur in this section over here. Okay, so therefore I can just discount that, and then therefore this is my new interval. This is now my new interval from here to here. Okay, so in other words, this is now my higher. x2 has now become my upper bound of my interval. So therefore, that's going to become x high. Okay, and now I need to define what x2 is. Well, I can define what x2 is using this formula here. Same kind of process as I did before, just rearrange it to find x2 is equal to. So just rearrange this. So again, just multiply through by x high minus x low. So x high minus x low. Okay, and I want to just find what x2 is equal to. So let's take this x low on the other side. So this is going to become then x low plus phi times my ratio of my interval. Okay, so in other words, you know, this should be right because x2, which will occur over here, say. So x2, which will occur here. Okay, so I've just found what x2 is equal to. Well, that distance will be measured from x low. So that distance will be measured from x low. So likewise, when we're finding x1, I measured it from x high. Oops, I measured it from x high. Okay, for x low, I'm measuring from for x2, I'm measuring it from x low. So x1, I'm measuring from x high. X2, I'm measuring it from x low. Okay, so that's just a formula for it. I'll write these formulas out again at the end. So I just want you to basically understand what the idea is, right? So let's have a look at this function value. Oops, go away. Let's have a look at this function value for x2. Well, to me, that function value for x2 looks roughly the same as the function value for x1. So therefore, all I just do, this is a really nice thing, I know therefore that the function value must lie somewhere between that interval from x1 to x2. So when I end up with the fact that x1 is roughly the same as x2, then therefore I just know that the interval, you know, the minimum value of the function, so the stationary point, the minimum value of this function, the stationary point, I know that therefore it must lie somewhere between the two. I don't know where it lies between x1 and x2, so therefore I just take the middle value. So I just take the midpoint of x1 and x2, so x2 minus x1 over 2, and that will be my stationary point. Okay, so that's all the idea is. Okay, so what again was my formulas for x1 and x2? So when I'm doing my updates, what were my formulas again? Okay, so I always kind of try and work it out. It's a nice, simple way of remembering it. Okay, so therefore I know the blue length. Okay, so the distance from x high to x1 must be the same as the distance as the red length, so the distance from x2 to x low. Okay, and that distance is phi times the length of the whole interval. Okay, so x high minus x low. Oops, x low. Okay, so therefore I know those intervals must be the same. So x high minus x low. It's just the ratio. It's just a you know, the whole interval. Okay, times by 0.618. So it's a little bit over half the whole interval. That's how long that distance is. Okay, well x1 is being measured from x high, right? That distance there is that distance there. So it's being measured from x high. So therefore it's going to be x high minus that distance. So minus phi times x high minus x low. Yeah? Whereas x2 is being measured from, where's it being measured from? It's being measured from x low, right? So x2 is being measured from x low, so it's x low plus, because it lies to the right, because x2 lies to the right of x low, so it's going to be plus, whereas x1 lies to the left of x high, so it's going to be minus. Okay, so it's going to be, so for x2 it's going to be x low plus that interval, the length of that interval, so it's x high, phi times x high minus x low. Okay, and that's basically all it is to it. So it's a nice simple algorithm, really nice simple algorithm for golden section search. Okay.